Okay, good evening, everybody.
Good evening.
And welcome to another session of organic chemistry. In today's session, we are going to finish our discussion of chapter 23. More specifically, we shall discuss the Michael reaction and Robinson annulation. But before we do that, we are also going to do the problems that you guys have just done in your quiz. And also, before we start, let me make a few announcements. I do want you guys to know that we have less than 2 weeks before the end of the semester, so our journey is almost over. What that tells us is that we need to do a lot of work between now and April 25. Okay? So on this coming Friday, we are going to have an online review session, and that online review session will be concerned with the problem set in chapter 23, that is on Friday, April 19 at 8 p.m. Also on Sunday, that is April 21st, April 21 at 8 p.m. we are going to have an online review session, and for this we are going to use the problem set from a previous exam number 4, and so that review session will be we are going to review for the exam number 4, which is scheduled for Thursday, April 25. I also want the graduating seniors to know that for the graduating seniors, your final exam is on Wednesday, April 24 at 6 p.m. in room G8 of the chemistry building. And then for the graduating seniors, you come back on Thursday, April 25 to take the exam number 4. So you have to take 2 exams back to back. This is for the graduating seniors. And finally, I want to remind you that the homework assignment for this week is due on Sunday, April 21 at 11 p.m. and that is our chapter 23, end of chapter 23 problem set. Okay, so for now, let us get our session started today. When we left on last Thursday, we were discussing Aldol condensation, intermolecular Aldol condensation, Claisen condensation, intermolecular Claisen condensation known as Dickman condensation. So today what I want us to do is to begin working on the Michael reaction and the Robinson annulation. And to do that, of course, before we do that, let us use the problem set that you guys have just taken in your quiz. Okay, so I have the first question here, which should be sort of like a review set of questions for you. Onyi, can you go ahead and read this question for us?
Provide the missing reagents for the following sequence of reactions. Okay,
thank you. Now, what we want you to do here, we have a sequence of reactions with missing reagents, and we want you to provide the missing reagent. Okay, so here we are going from this cyclohexene. We need to open up the cyclohexene chain and make a diester. So what reagent do we need here? What is it? Okay, Natalia said KMNO4, potassium permanganate, very good. So for this 1C, that is potassium permanganate in acidic medium, that would be C. Okay, so what this does, the potassium permanganate will clip the carbon-carbon double bond to give you 2 carboxyl group, right? Okay, and then once you do that, about 2D, what reagent do we need for 2D? Esterification? Okay, very good. So for 2D, you say we need a Fischer esterification? Okay, very good. So therefore, what kind of alcohol do we need? Ethanol. Okay, very good. So we need ethanol in preferably in some concentrated acid like sulfuric acid or sometimes phosphoric acid. Okay, very good. So what this does is to do after you form the diacid here with potassium permanganate, and then you use ethanol in acidic medium to form the diester. Okay, very good. That's about 1E right here. What reagent do we need for this? 1E. Here, what are we doing here? What type of reaction is this? Claisen? Okay, very good. Okay, this is Claisen condensation. Specifically, this would be intramolecular Claisen condensation. What other name do we call this? Call it Dickman condensation. Very good. Okay. So what reagent do we need? Ethoxide. Okay. What does the ethoxide do? It forms the enolate anion. Okay. Okay. Very good. So the ethoxide, we could assume that the ethoxide will form the enolate anion. Let me number this. 1, carbon 2, 3, 4, 5, and 6. So we could assume that the ethoxide will form enolate anion on carbon number 5, right? And once you form your enolate anion here, that will attack that nucleophile will attack the electrophilic carbonyl on carbon number 1. Is that correct? Okay, very good. And so therefore you are going to form a 5-member ring, and that is what we have here. Okay? Okay, now what is, okay, that is 2E. So you say ethoxide here. Change the color of my pen. For here, you say you are using ethoxide, of course, in ethanol as solvent. Okay, now what is 2F? What is 2F? Hydronium ion? Okay. Now, why do we need hydronium ion?
To stop the reaction.
Okay, very good. You guys are ready for the exam number 4. It seems like. Okay, to stop the reaction, exactly. Okay. The hydronium ion is there to stop the reaction because at the end of the nucleophilic acid substitution using the Claisen condensation, you are going to form an enolate because you see our ethoxide present in solution. And then to protonate the enolate, you add the hydronium ion. Very good. Okay, about, okay, so that is 2F. And this is 1A right here. About 1G right here. What are we doing here? Understand what? Okay, hydroxide. Okay, what does the hydroxide do? You say hydroxide? Okay, okay, look at what, okay, very good. Okay, what do we need to do here? You say hydroxide or LDA? Well, what are you trying to do? Keep in mind, this is what we want here. We want to attach, we want to do an alkylation, right? Okay, so what do you need? You need a base, and then you need an alkylating agent. What base do you want? Ethoxide, LDA, right? Okay, let's use LDA. Okay, so LDA, lithium diisopropylamine. Okay, so that would be 1G. The LDA, what the LDA will do, of course, to deprotonate this hydrogen here to form the inolate anion, and then you follow that up with the 2H. What do we need for 2H? Alkylating agent. Okay, very good. Methyl bromide. Okay, that's good. Okay, so you use methyl bromide. Then, about I'm sorry. Okay, now we need to do something else. Okay, LDA, what LDA will do, form the inolate anion, and then the alkylating agent comes in, we do that. So let me take this off. Sorry about that. This is not 2H. This here is part of the 1G right here. Okay? Okay, so 1G is a combination of LDA, we say step 1, and then we say step 2, so that would be 1G. About the 2H, what happens after that? Okay, in other words, this is what you are going to get. Let me do this. LDA with methyl bromide, you get this. Okay? Now what happens? This is where we want to go. Then what happens? What would be 2H at this point? Hydronium ion, exactly. You now do hydronium ion. What does the hydronium ion do? Hydrolyze to carboxylic acid and then heat. Okay, very good. And then we do decarboxylation. Okay, so I think most of you guys you know your reagents, so that tells me you are getting ready for exam number 4. Okay, so let us go to the next one. Any question on this? Okay, Natalia, go ahead and read this for us. Let's hear your voice.
Unit 2,7-octet-diethanol, sodium hydroxide, and ethanol, right structures for the 2 Aldol condensation products, one of which is methyl ketone. Right, and mechanism for the formation of the methyl ketone product.
Okay, thank you. So what they want us to do here, they want us to use 2,7-octane-dione, 2,7-octane-dione, and to do an intra. In this case, we want to do an intra. I told you you need to do an intramolecular Aldol condensation. Okay. Okay, so the first thing we need to do is to know the structure of 2,7-octane-dione, right? Okay. So let us start with this. Okay, let us go ahead and number this molecule here. This carbon 1, let's call this carbon 1, 2, 3, 4, 5, 6, 7, and 8. So that would be 2,7-octane-dione. Is that correct? Okay. Now, we have to do Aldol condensation. We have sodium hydroxide. In ethanol as solvent, and they told us we need to form 2 products. Okay, we need to form two products, and one of the products will be a methyl ketone, and you are now asked to give the mechanism of the formation of the methyl ketone. Okay, so what will be the two products? What will be, okay, now let me ask you this. Hydroxide, what does the hydroxide do? It forms enolate on what carbon atom? Okay, you want to form enolate on carbon 1?
3 for the methyl ketone.
Okay, you need to form two products. 3, okay. If you want to form enolate here, okay, form enolate there, and therefore your enolate will attack what carbon? Carbon number 7. Very good. So your enolate will attack carbon number 7. Right? Okay. Okay, so therefore, let us see what will be the size of this chain here. We're going to form a ring, cyclic molecule. How many? 5-member ring, okay. That is 1, 2, 3, 4, 5. It's a 5-member ring. Okay, so therefore. If we say that, we say this is, therefore this will be here. Okay, and therefore this will be, let us see here, this will be here. Would that be correct? Okay, and therefore this will be here. Let us see, is that correct? No. Not? Oh, okay. Okay, where will it be then? Where will it be? It will be conjugated, right? Very good. So it will be here, right? Very good. Okay. Just checking to see whether you guys are sleeping. Okay, so it will be conjugated, just like Natalia said. Very good. And then the methyl will be where? It will be here. Okay. Okay, so let us number the carbons. Based on this numbering here, right? So this is carbon 1, carbon 2, and this is carbon 3. This is where we form the enolate. And then that was the nucleophilic carbon. And this will be carbon 4. This is 5. And this is 6. And this is 7. This was the original carbonyl. Okay, and this is 8. Do you agree with that? Yeah. Okay. And so that is structure number 1, or product number 1. It is also a methyl ketone. Okay. Okay, what will be product number 2? Where is the enolate coming from?
From number 1.
1? You want to do enolate on carbon 1? Okay. Let's try that. Okay, let us assume that we form the enolate here. Okay, we remove we deprotonate that methyl carbon there, and so we form enolate here. And then what happens? Once we form the nucleophile on carbon number 1,
it attacks carbon number 7.
Attacks carbon number 7. Very good. Attach this here. And of course this will go here. Okay? So therefore, okay, you are going to form a ring. What is the size of the ring? 7-member ring. Okay, very good. So we have this. If we say this is our carbonyl here, right? And therefore, if this is carbon number 1 right here, so therefore we have this right here, and then this will be here. Let us go ahead and label our carbons. Okay, based on this numbering here, okay, this will be carbon number 1, right? 2, 3, 4, 5, 6, and 7, and then 8. Okay? So far, so good. Okay? Okay, now the next thing you need to do is to write the mechanism for this product. Can you guys write the mechanism? Okay, so we could move to the next question.
Yes.
Okay, very good. Anybody say no? Move to the next question. Is that what? Write the mechanism. Oh, okay. I know what Valerie is trying to do. She's trying to slow me down. She's trying to. I know what you're trying to do. You know it, but you just want to see whether you guys can be slowed down, right? Okay, let's do the mechanism. Okay.
I'm not that smart, so I need you to do it again.
No, I know you better than that. Okay. Let us write the mechanism for this. Okay, so I'm going to take this out. Okay. Okay. For the mechanism to go from here to this methyl ketone, of course, we say we are starting with hydroxide, right? And if we are starting with hydroxide, what do we have? We have, let's see here, take this out. We want to form our enolate on carbon number 3. So we have these 2 hydrogen here, these 2 alpha hydrogen. The hydroxide comes here, picks up this proton, right? And then you are going to form your enolate, because once you abstract the proton, the carbon hydrogen bond, the electron will be left on these carbons here. So you're now going to form an enolate anion. Okay. Okay, now what happens after that? What happens? Let me go ahead and number this here. This is 1, 2, 3, 4, 5, 6, 7, and 8. What happens? Carbon number 3 attacks number 7. Very good. And this pi electron goes to oxygen. Okay? Okay, so once that attack takes place, we know we are forming a 5-member ring. Okay, and that is this carbon here, carbon number 3, attack this here, right? So there will be here, there will be negatively charged oxygen, the alkoxide anion, and then you have the methyl is here. Is that right? Okay. So at this point, in the Aldol reaction mechanism, we are going to protonate this alkoxide with water. We have water here. Keep in mind, when you abstracted the hydrogen from here, you did form water right here. Okay? So this comes in, abstract the proton from water. Now you regenerate your hydroxide. So now we get this. That and that. Okay. Keep in mind we also have hydrogen here. We have hydrogen here. Plus at this point we also have hydroxide. Okay, so far so good. Now what happens next? What happens next? At this point we have from our aldol. This is an aldol. Okay, what is going to happen now? We are going to lose. If you apply heat, sometimes, very often you may not even need to apply heat for this to go. So you could think of this hydroxide coming here, pulling off this proton, and so doing, releasing electron to form the pi electron here, and at the same time the hydroxide will leave. Now this is one of those few occasions when the hydroxide actually acts as a living group, because we are forming an alpha beta unsaturated carbonyl compound, okay, which is very stable, which is this right here. Okay, you see the mechanism? What we just given you here, that is the complete mechanism for the Aldol condensation reaction. In this case, an intramolecular Aldol condensation. Okay, so let us go to the next one. Okay, Ines, go ahead and read this course.
Using ethyl acetate and ethyl propanol provide a mechanism for the Claisen condensation reaction.
Okay, thank you. Okay, so here, using ethyl acetate and ethyl propanoate, they wanted to provide a mechanism for a mixed Claisen condensation reaction. Okay, in this case, you could use any one of them as a source of your nucleophile, and any one of them as the source of the electrophile. Okay, so which one do you want to use for the nucleophile? Ethyl acetate. Okay. Okay, so Abra, you say you want us to use ethyl acetate, so let us do that. Okay, now to form your nucleophile, what do you need? Ethoxide? Okay, very good. Okay, then what is going to happen? Okay, since they want us to give the mechanism, let us show the abstraction of one of these hydrogen by the ethoxide. So this comes here, pulls off this proton, and thereby leaving a pair of electrons on the carbon. So now you form your enolate anion. Okay, then what is the next step? You want to use the propanoate as the source of the electrophilic carbon. Okay. Okay, so now carbon, this comes here, the nucleophile comes here, attach this electrophilic carbon right here. Okay, and that will lead us, let me change the color of this so that we could see this better. Let's make this green. I'm sorry. Okay, so we have this as intermediate product. And now what happens after this?
Regeneration.
You go to reform the carbonyl, right? Okay. So this is an example of nucleophilic acyl substitution reaction. Acyl substitution reaction. Okay. And once you reform the carbonyl, and then the ethoxide will leave. So that's the carbonyl which has been reformed. Plus you also form ethoxide right here. Okay, now what happens? Once you form the ethoxide and this here. Okay, the ethoxide will abstract this proton here because it is very acidic, right? Okay, so let me take one of these out. Ethoxide comes here, pluck out this here, thereby forming another annulate anion. And then after this, what happens? We add hydronium ion, exactly. Now we add hydronium ion. Okay, so the hydronium ion will stop the process by protonating these annulate anions here. Okay. Then we have this final product. Okay, so what we're giving you here, this is the mechanism of the Claisen condensation reaction. Okay, so I think we've done all of the three problems. So now at this point, let us finish up on chapter 23, after which we are going to start chapter 24. Okay. You don't believe that, eh? Okay. Okay, let us see here. Okay, so at this point, let us finish up chapter 23 with a discussion of the Michael reaction and Robinson annulation. Okay. Conjugate addition reaction. I'm sure you guys remember that we did this when we did chapter 14. We did in several of the chapters before now. So this should not be new to all of you. Remember when we add this molecule here, we have a conjugated carbonyl system. Okay, alpha beta unsaturated carbonyl system. And if, for example, you take this, take your nitrite, and you add, what happens here, this nitrite acts as a nucleophile, because we know that this beta carbon here is electrophilic as a result of, if you look at the resonance contribution for that molecule, move this electron to here. Let me take this out of here for now. This will get this inlet here, and this here becomes positively charged. We could also write additional resonance structure, in which now we move this here, this pair of electrons to here, and this pi electron to oxygen. Now we have this. Still this carbon, the beta carbon is still positively charged. Keep in mind this is the alpha carbon here. This carbon here is the alpha carbon, and this carbon here is the beta carbon. Okay? So this beta carbon is electrophilic. Attracts nucleophile. Okay, so we all know that. Okay, because of that, if you have a nucleophile, the nucleophile in any alpha beta unsaturated carbonyl compound, the nucleophile tends to attack the beta carbon, and that's what we are going to have here. Okay. So in this case, this comes here, attack this here. So doing, of course, this goes here. And then what do we get? Okay? And then when we add the source of proton, in this particular instance, we could add HCN or hydronium ion. We protonate this here. Of course, there was another hydrogen there before. Okay, this type of reaction we refer to as the conjugate addition reaction. And specifically, we call this a Michael addition reaction. Okay, called a Michael addition reaction. Other examples. Supposing I have this. Let us say I have this here. Even an amine could act as a nucleophile here. Comes here, attack this. Electron comes here, and then what do we get? Okay, this nitrogen at this point, because we are starting with a neutral nucleophile, is positively charged. And then what is going to happen? There will be an intramolecular hydrogen transfer, right? The enolate picks up this proton here and thereby releasing the electron to nitrogen. Okay, so therefore you form okay. So that is another example of conjugate addition reaction or Michael addition reaction. So there is no limit to what we can do here. Only our imagination is the limit. For example, I could take the same molecule here. I could take the same molecule I could take ethyl acetoacetate, I'm sorry, malonic ester enolate anion. Okay, assume that we generate this enolate anion here. I could do that with this here. What do we get? Step 1. Okay, and then step 2, hydronium ion is added. Okay, of course this here, you also have a sulfide here to generate the enolate from the malonate, right? You get this. So you see what we can do here. Okay, now you know what you can do with these products. We could hydrolyze this to form the dicarboxylic acid. Okay, if you want, we could do the carboxylation, and then in the process, we end up with this final product. So if you see here, your imagination is the limit right here. So we could end up with this product. So it's carbon dioxide. That is after hydrolysis. Okay, then we apply heat. Get this. Okay, so these are examples of Michael addition reaction. Now, what I want to do now, let us now combine the Michael addition reaction and the Aldol condensation to begin to make very complex molecules. You recall I told you when we started this section that at the end of this chapter, you should be able to make this type of molecule. Steroids, right? This is adrenosterone, so you should be able to make this type of molecule. So now, you guys have now become organic chemists. Now let us see, can we do that? Let us see. Okay. Let us use what we call Robinson annulation. Robinson annulation. Okay, what time do we have? Okay, I need to do this and finish chapter 24. Okay, let us look at Robinson annulation, okay? Supposing I take this. By now, you guys know how to make this molecule. You know how to make that molecule by now. Right? Okay, I'm sure you do. Okay. Supposing I take this, right? Okay, I take hydroxide or ethoxide or LDA. Okay, I form an inolate anion. I then take that inolate anion and react with this molecule here. At this point, what type of reaction do I want to perform? This inolate reacting with this, what kind of reaction do I want to perform? Michael addition, right? This here reacting with this, okay? Oh, what is it? Okay. You also know how to make this compound. How will you make this compound from aldol condensation? This compound, you could make this if you have formic acid reacting with acetone, right? That's an aldol condensation product. That will give you that. Okay, that will be an aldol condensation product. Because you form your nucleophile here, and that attacks this here. This will be a mixed aldol condensation. You follow that. Okay? Now, so this comes here, inolate comes here. We're now going to perform a Michael addition. This comes here, and then what do we get? We get this. Change the color of my pen. Okay, do you see that? So far so good, right? Okay. So we form this inolate here, and then once we form that inolate, keep in mind also we have water formed right here as a result of forming this inolate here, this hydroxide. Now, you could now take this in water to protonate this here. And then what do we have? We have this. Plus hydroxide. Okay, so let me make this blue so we know. Okay, do you follow that so far? Okay. Now what I've done here is the Michael addition reaction. Now this molecule now is set up to do an aldol condensation. This here comes here, hydroxide comes here, attracts the proton, form another annulate, and what do we get? We get this. Okay. Now, what do you think is going to happen now? Okay, attack of the nucleophile. Nucleophile will attack this electrophilic carbon right here. Of course, you see I have this here. Attack this here, goes here, and then we form this. So now we form the aldol. From the aldol. Oh, by the way, okay. Assuming that we protonate this. Okay, assuming that we are going to protonate this. Once you form the alkoxide, you protonate the alkoxide, then you form the aldol, and then when you apply heat, at this point, we form this product here. Okay. Now this, what I've just given you here, of course this is the final product. What I've just given you here is what we call Robinson annulation, which is a combination of Michael additions and aldol condensation, which is combination of Michael plus aldol. And annulation means we are forming a ring formation. So anytime we do Robinson annulation, we are forming a ring. Okay. Now if you look at this, okay, let me go to a new page. That molecule we just given you, which is this here, okay, is what we call Weiland Maisha ketone. And this is the ketone that is a precursor for most of the steroids that we have in commercial use today. I'm sure you guys know the importance of steroids. Most of the hormones that make us what we are, both the female and the male hormones are steroids. So anyway, so this molecule here, this ketone is very important. We could write it this way. Essentially, this in this way. If we turn it around, If you turn it around, it is the same molecule right there. Now, supposing we now take this ketone here. Supposing we take that. This is the last thing I will give you. And then we react with this here. Supposing we take that. We have, say we take hydroxide or a toxide or a base. We pull this proton from here to form an inulate here. Supposing we do that, we take this molecule here, which you guys can make. We could do what type of reaction on this? What type of reaction is that? That's a Michael addition. We do a Michael addition. So let me give you the complete product on this Michael addition. Supposing we do that, then we have this. That would be the Michael addition product. That would be the Michael addition product. Okay? In the presence of water, of course. That would be your Michael addition product. Now, supposing we now take another hydroxide. We now want to do an aldol. Okay, we do an aldol. Remove this proton here. Imagine if we remove this proton here, right? And then what do we get? From an inulate, and that inulate attacks this carbonyl, and then we do dehydration of the aldol. What do we get? We get this. So you guys have now made a very complex molecule, a steroid, which is one of the more complex molecules that you can make as an organic chemist in a general chemistry, introductory organic chemistry class. Okay, so we have this. We have that. We have this here. We have this here. We have this here. This is here. Okay, if you look at this, what do we have here? This here, let me label this here, let us say this is 1, 2, 3, 4, and that is this one here, 1, 2, 3, 4. Of course, once you form the aldol, that means you are going to form a conjugated system. Okay, so now starting from very, very simple molecule, we could actually make very complex molecule like a steroid. And all of this here, what have we done? We use simple reactions like Aldol condensation, Michael addition reaction, essentially doing deprotonation, nucleophilic addition, and here what we've done, we make this as steroid. And I think our time is well spent. Oh, no, we're going to 2 more minutes. Okay, so when we come back, we are going to start with chapter 24. So enjoy the rest of your evening. Yes. Yes.